You ever see one of those massive dams and just wonder, how do we take all that incredible raw power of rushing water and turn it into the electricity that powers our lives? Well, the secret isn't just about the water. It's about finding the perfect machine to harness that power. And today, we're going to pull back the curtain on the amazing science of how to choose the perfect hydropower turbine. So here's how we're going to do it. First, we'll get to the heart of hydropower. Then we'll look at the two different kinds of rivers an engineer might be dealing with. We'll meet the two main families of turbines, uncover the secret number that makes the choice crystal clear, and then we'll actually crack a real-world case together. Let's get into it. Okay, so picture this. You've got a source of falling water. You can just feel the potential energy there waiting to be used. But how do you actually grab it? Well, it takes something way more sophisticated than just a simple, old-fashioned water wheel. And that something is the turbine. Its whole job, its entire purpose, is to take all that energy from falling water and turn it into rotational power, a spinning shaft that can drive a generator. This machine is really the hero of the whole hydropower story. But here's where it gets tricky. Turbines are definitely not a one-size-fits-all kind of deal. There are tons of different designs, and if you pick the wrong one for your river, you're literally just letting massive amounts of clean energy slip through your fingers. So how on earth do engineers make the perfect choice? Well, to solve this puzzle, engineers act like detectives, and the first thing they do is examine the clues at the scene, which is the river itself. Turns out, you can boil down the personality of any water source to just two key things. On the one hand, you might have what's called a high-head, low-flow site. Just imagine a really tall waterfall that doesn't have a whole lot of water going over it. It's kind of like a super powerful focused jet from a pressure washer. But on the other hand, you could have a low-head, high-flow situation. This is more like a huge, wide, slow-moving river. Not much of a drop, but an absolutely massive amount of water. And as you can guess, these two scenarios need totally different solutions. And that brings us to our turbine families. See, there are two fundamentally different ways to capture water's energy, and each one is designed for a completely different kind of river personality. First up, you've got impulse turbines. The idea here is simple. You shoot a high-speed jet of water at these little buckets on the turbine, and it just pushes them around. The easiest way to think about it, it's like blowing on a pinwheel to make it spin. Then you've got reaction turbines. These are completely different. They sit fully underwater, and as the water flows over their specially shaped blades, it creates a pressure difference, just like on an airplane's wing. This creates lift, and that lift is what causes the whole thing to rotate. It's a lot like how a spinning lawn sprinkler pushes itself around. All right, so let's meet our main suspects. This table lays them out perfectly. You've got the Pelton on the left, that's our impulse turbine, a real specialist for those high-head sites we were talking about. Then you've got the Francis and Kaplan, which are both reaction turbines. The Kaplan, way over on the right, is the undisputed master of low-head, high-flow situations. And the Francis? Well, think of the Francis as the versatile all-rounder. It can handle just about everything in the middle. So we have the clues from the site, the head and the flow. And we have our lineup of turbine suspects. But how do we make the final definitive match? Well, it turns out engineers have a secret weapon, a single piece of evidence that cracks the case wide open, every single time. Yep, it all comes down to one single, powerful number. A number that takes everything we know about the site and the power we need and distills it into a unique code. That number is called specific speed, or NS for short. Now don't get hung up on the name. Just think of it like a personality profile number for a turbine. A low specific speed tells you it's a turbine built for high head and not much water. A high specific speed means the exact opposite. So here's the key takeaway. You calculate the specific speed for your site, and that number points you directly to the perfect turbine. And this is how they do it. It looks complicated, but the idea is simple. Engineers take the speed the rotor needs to spin, that's N, the amount of power they need to generate, P, and the site's head, H, and they plug them into this formula. What comes out the other side is that one magic number that tells them exactly what they're looking for. Okay, we've got the theory, we've got the formula, let's put it to work. We're going to take this secret number and use it to solve a real-world hydropower problem, just like an engineer would on the job. All right, here's our case file. We've got a site with a 25-meter head, kind of in the middle. It needs to crank out a serious 7,200 kilowatts of power, and the generator has to spin at 200 RPM. So, the big question is, which turbine gets the call? Pelton, Francis, or Kaplan? So job one is to find that critical piece of evidence. The engineer takes the numbers right from the file, a speed of 200 RPM, power of 7,200 kilowatts, and a head of 25 meters. And they plug all of that right into the specific speed formula. They run the calculation, the math does its thing, and all that site data, the head, the power, the speed, it all gets boiled down into one simple, elegant clue. Our magic number. And there it is. The magic number for this project is 38.54. This is the fingerprint of our solution. This one number holds the key. Now for the final and honestly the easiest step. They just take this number and check it against a standard chart that shows the operating ranges for each of our turbine suspects. It's basically like matching a fingerprint to a police database. And here's that database. Take a look. The Pelton Wheels range, it only goes up to about 51. The Francis turbine handles that middle ground, from 51 up to 255. But our number, 308.54, it falls smack dab in the middle of that last range, 255 to 860. And who owns that territory? The Kaplan turbine. That's our match. Case solved. In the real world, engineers often use an incredible tool like this one. It's called a nomogram. It's basically a master chart that puts everything, power, head, speed, and that all-important specific speed, all in one place. It lets them see the entire process visually and find exactly where their project fits. It's pretty cool. So when you really think about it, what seems like just a fancy water wheel is actually so much more. It's this perfect blend of physics and geography, a piece of technology that's custom designed and perfectly fit to the unique fingerprint of one specific spot on one specific river. It's an amazing bit of engineering, isn't it?